because one of the things you have to do, one of the things we learned in section 2.4 is how to find local max and local min. So where do we start to find local max and local min? Set what equal to 0? The derivative, right? Because the local max is when the slope is 0. So we do the derivative and we set it equal to 0. So what's the derivative of x cubed? 3x squared. What's the derivative of 3x squared? 6x to the first. What's the derivative of constant k? 0. Any constant, the derivative is 0. That goes away. Oh, that's nice, because now I don't have to worry about it. Now we can pull out a 3x. This looks very much like a problem we were doing the other day. And we get this. And so x is either equal to 0 or x is equal to 2. So, obviously, this graph is not accurate. It must look more like this graph. Right? And here's 2. Right here, and here's 0. I must have a max. Now, we don't, I know that this is going to be a max or min because I know that this is a cubic, and I know a cubic with a positive leading coefficient starts by going up, and then, you know, it goes up that way like that. And so my two places where the slope is 0 are going to be at 0 and 2, right there. And I don't know where they are for sure, but I'm just going to assume that I got 3 roots. I could test this. Well, we can just do it real quick. Let's do a number line, right? Because the next thing we talked about was do a sign analysis, right? We said do a sign analysis. See where this local max and min are. So let's do that. So let's put 0 on here. Let's put 2 on here. This is really good practice right now. Okay? And so now we got, okay, there's a -1, there's a 1, there's a 3. Now imagine this problem was simply, instead of what it says, imagine this problem is find the local max and min. Okay, where are their local max and min? That's for sure something you're going to have to do. We did it at number 19. You guys have to do it on number 20 in the homework, or 21. I can't remember whichever one. You guys have to do number 20. I think the same thing. Find the local max min. So that's what we're doing. So I'm going to take -1. Here's my y prime I'm going to plug into right here. I get a negative here, negative there. That's positive. Put a 1 in. I got positive and a negative. Put a 3 in. I got positive, positive. So this graph's going up, then down, then up. Okay. Got it. Okay, that's what I knew it did because this was a cubic, so that was easy. But this tells me for sure got a local max, got a local min. Okay, but now let's go to the next part. Okay, so the next part is what are the k values? Well, how would I know what this y value is right here? How would I know what this y value is right here? Oh, come on. You're making it way too hard. You act like you haven't been in school for 5 days. Plug into the original, right? So this is where sometimes people get confused because we've got so many different equations we can plug it into, we forget. Well, think about what you're trying to get. If I was trying to find out if the graph was concave up or concave down, I'd want to plug numbers into the second derivative, right? Because when the second derivative is positive, it tells me if the graph's concave up, second derivative negative. So if I want to plug into a second derivative, if I want to find out my concavity, that's where I plug into. If I want to tell if the graph's increasing or decreasing, I want to plug into the first derivative. Because if it's positive, f is increasing. If it's negative, f is decreasing, right? But if I want to know what the point on the graph is, then I plug into the original, right? I plug into the original. So we put a 0 into the original, we get k. So this is the point 0k. And then I put a 2 into here, that'd be 8. 2 squared is 4, so 8 minus 12. So this is -4 plus k. So this is the point 2, and then -4 plus k. Right? So those are the y values. So that's the key thing. So when will this have just one root? Well, one time it'll have just one root when this goes all the way down where? Below the x-axis, right? So when k is what? So one root or one x-intercept is going to be when k is less than 0. Right? For sure. When k is negative, that means this graph is going to be down below here. Right? Now, also, it'll have one root when this y value here goes up. Right? So when this y value, which is what? -4 plus k is what? Greater than 0. Which means when k is greater than 4. So when k is less than 0 or k is greater than 4, I know I'm going to have one root. Right? So that was the thought process on that. I'm going to have one root. Now, when am I going to have 2? Well, that's when this is equal to 0 or when this is equal to 0, right? So I'm going to have 2 roots. I'm going to have 2 roots when k is equal to 0 or when k is equal to 4. So when k is equal to 0 or equal to 4, I'm going to have 2 roots. And then when will I have 3 roots? When it's between 0 and 4, right? So when it's less than 0 or more than 4, that's going to be shifted up too far or too low on 1. But so when k is between 0 and 4, then I'm going to have my 3 roots. Okay? So that, that part, that we haven't seen that before. It makes it's a really good problem. It really makes you think about it. But the key to that problem is understanding that, okay, I've got this cubic. The most it can have is 3 roots. It's the shifting is what k is. In fact, the key part of that when it shifts up and down is where the local maximums are. So that really, see, we're really at the point. So the quiz is going to focus on more of the stuff in black where how do you find a local maximum, right? Because that's where we're at right now is the beginning of that. But you can see where we're going to go later on is we'll get into problems where as we analyze the problem and think about the problem, we're going to realize that the local maximums play a key role. So we're going to want to find the local maximums and then use that information to finish and solve the problem. Okay, so that's a little, that whole problem's a little beyond where we're at right now. But finding the local maximum, doing a number line, that kind of stuff, we'll be able to do that for sure. Okay, what else? 34. Suppose that big F, I don't have my glasses today, so I'm in big trouble. What's that say? Big F prime is equal to big G prime for all x. Is it possible that big G of x is equal to big F of x plus, what's it say?
Plus x.
X? What do you think? Yes? Jace? Why are you saying no?
Took away the x. Then
How? Is there something we can do to this to show that it's no? You're right, the answer is no. How about this? How about if I take this and just do the derivative of both sides? What's the derivative of big G? Or little g, but we're using the prime, so we'll just call it big G. What's the derivative this side? Big F prime. What's the derivative of x? What's the derivative of 1x to the first? Bring down the 1. X to the 0, which is just 1. Remember, the derivative, what's the derivative of 7x? 7. Derivative of 3x, 3. 4x, derivative, 4. Derivative of 1x is just 1. Okay? So if this is true, then G prime's got to be F prime plus 1. So G prime can't be, G prime's always going to be 1 bigger than F prime, right? So that's why it's not. Okay, now what if this wasn't an X, though? What if that was an 8? Now, what's the derivative of 8? Right? So when you said if this was just big, if the X wasn't there, yes, big G would equal big F. But remember we talked about how because that's, if we go from f prime to f, or g prime to g, we're doing the, what's it called? Antiderivative. Remember we talked about how that vertical shift, there's a lot of different functions, right? So if I have 2x, what, if that's big F prime, then what was big F? X squared, or x squared plus 1, or plus 2, or x squared. Remember when, didn't I do like a big C, like for a constant? All of these, if you do the derivative, they all equal 2x, right? So the idea here is that if you have two graphs that have this, if you have two functions that are the same derivative, they don't necessarily have the same antiderivative, but they can only be different by what? A constant. They can only be different by a constant. So if we have, Jace, back to what you said, when you said if the x isn't there, sure. If big F prime is equal to big G prime, though, it doesn't mean that big F has to equal big G, right? But they have to be almost equal. They have to be exactly the same except for a constant added on. That's the difference. Okay, so that's what 34 is. Okay, what else? And 3 through 12, if you're studying for your home, for the quiz and stuff, a problem like 3 through 12, which we already went over before Thanksgiving, right, would be good one to review. That's chart stuff, that's the chart stuff, and that's where they give you the little f graph, and they talk about big F, but remember, that's just like in chapter 1 where we had the f prime graph, and I talked about F, right? So that's just chart stuff and all that, but that'd be good to review, because we introduced this notion of big F, and how, we go big F, then little f prime, then little f double prime, then, big F prime is the same as little f, and big F double prime is the same as that, and big F, I guess, triple prime would be that. But, okay, so just the chart and reviewing that would be good. All right, anything else? Okay, well, I think something we can come up and talk about. So, let's review the quiz. Now, this is 2.3, that's 2.4. 2.4, though, the only thing 2.4 added to the mix here that's not listed here was that local max min that we kind of already went over, the sign analysis, the plus minus, doing the sign number line thing, and then also the big F notation, right? So that's really all we added in 2.4. Okay, so if we focus here on 1, 2, 3. And I kind of written this up here the other day. But so in 2.1 is where we got the long way. And so we definitely want to practice that today. This whole idea of limit, we want to spend a lot of time doing that because that's a big part of what we've been doing here. Okay? So we want to make sure we really hit on that. So that was where we first got the notion that the slope at a point is two close points, so A and A plus H, we pick a point and then another point close to it. And then we let the 2 points become 1, and that's what the limit does. H goes to 0, which H is the distance between the 2 points. And so as that goes away, then the 2 points become 1, and we have the slope at 1 point. In 2.2, then, instead of f prime of A, we did f prime of x. So what that allowed us to do is then just get a formula. So that's when we learned that the derivative of x squared was 2x. Or the derivative of x cubed was 3x squared. And that was the power rule, right? That was our nice shortcut. Now that only works when you have x raised to a numeric power. Doesn't help us on e to the x, doesn't help us on sine x. So those rules we're just going to have to memorize the derivative, and we've done a little of that. So you're going to have to do some power rules, some shortcuts, and there's a few problems in the book that you can review. I've got a few problems in practice there, but that's just bring the power down in front, right? And maybe I've probably got a few of them we can do. And when we did that section, there were some where you first had to do a little algebra first. We talked about splitting apart a fraction. If you got a prop, if you were having to do like x squared plus x over x, and you wanted to do the derivative of that. Well, the first thing you need to do is split it up, or bring this x up on top. I don't care how you do it. But realize that this is just x plus 1. So you'd first have to simplify that. Yeah, I picked kind of a strange one, but you'd first have to simplify that, and that'd be your f. Now, if you want to do your f prime, well, that'd just be 1. Right, now if you want to do your derivative, now you do your power rule on that. So sometimes it might be written in a way that you have to first simplify it before you can then do your power rule. Okay? And remember, if two things are multiplied, if you have x squared times x cubed, you can't do those individually. You first have to make that x to the 5th. Then you do your derivative, 5x to the 4th. Right? So sometimes you have to multiply some things together, do a little algebra to it before you can do your power. Okay, then we got into limits. This will be a big part of the quiz, so we're going to talk about that. We had 3 different ways where we could do limits. Obviously, if you just have a graph, if you look on page, well, let's turn in your book if you're not there already. If you look at page 111, that's a great page to look at some problems there on page 111. So if I give you a graph like that, be able to answer some limit questions. Well, that's just do the cars meet. Do the cars meet? We don't care if there's a hole there, but the cars have to meet. If they meet, whatever y value they meet at, that's the limit. Okay? If they don't meet, if there's a break there, there's a gap, right? Then the limit doesn't exist. So if you have a graph, pretty easy. On that worksheet, the worksheet I gave you today on the front, they give you a graph. And then I think that on problems 3 and 4, they want you to graph. It says you may use the provided graph to sketch the function. So you could graph it on your calculator. That's fine. I'm not going to make you graph. One's necessary. Unless it's a piecewise. If I give you a piecewise like number 1 or number 2 on that, or number 1, I guess. Number 1, maybe, to graph something similar. Or on 5 and 6, you could take it. One of those you wouldn't have to do a graph. We talked about that. You can just plug in values. If you got a piecewise, it's going to break wherever it changes. On number 5 there, something weird's going to happen at 0 probably, or at 3, because that's where it changes from one graph to another. And then you just check to see if it's got the same y values and so forth. So we did that. Okay, algebra. That's the back side of that worksheet. So that's bow tie, conjugate, factoring, get your limit that way. What do you do? Oh, well, the first thing you do is plug in, right? Direct substitution, right? And what's going to happen most of the time when you plug in? You're going to get 0 over 0 most of the time. Now, what if you get 6 over 0? What do you say? Does not exist, right? For right now, if you get 6 over 0, it does not exist. You get 0 over 0, you keep going, right? Keep going. You factor, you bow tie, you do something, okay? And then you may get an answer. Okay, so you never stop with 0 over 0, right? And if you get 6 over 0, it does not exist. But 0 over 0, you keep going. Then we talked about the table. We'll review that with one here a little bit. And then we had the definition of a continuous function. That was, sorry, I kind of got ahead of myself. Okay, so yeah, we had the thing about continuous function. Let's talk about the limits here a little bit. Again, let's just review this if you want to get this down. So with algebraic limits, so the graphing ones are pretty easy. You just see do the cars meet. And with the calculator tables, that's pretty easy. You set up those limits, or they're set up for you. You put it into your graph screen on your calculator. Go to your table, Control T, go to your table, right? We'll do that in a minute. And you can see where the cars are meeting based on the table. Okay, so the one we got to probably do a little practice, more practice on, is this. So algebra limits, you start with direct substitution, see what you get. If you get a number, you're probably done. If you get 0 over 0, which is what's going to happen most of the time, you keep going. And then and that means by keep going, it means you're either going to factor and cancel, you're going to bow tie, you're going to do the conjugate, some algebra technique. Those are the 3 we need to be able to do. Then you might get an answer after you do that, or you might get like 4 over 0 or something like that, and then just say does not exist. Okay, at that point. And then, like I said, that may give you a graph. So if you get something like that, it does not exist, right? You got a break in the graph like that. On a piecewise, it does not exist. Now, if you don't have the graph, you just have the piecewise, and let's say this was at 2, right? The break was at 2. You plug 2 into the one, plug 2 into one of them, see what that y value is. Plug 2 into the other one, see what that y value is. If you get the same y value, it means they meet. It means they meet. You get 2 different y values, it means they don't meet. Right? So it's not like you have to have the graph. You can plug in to a piecewise and see if they meet at that spot. Okay, so that's kind of the idea of the limits. And then we talked about the definition of continuous. So this should be in your notes already. I'm going to write it again, it's fine. So what I might do on a piecewise graph, like on page 111, all of those graphs on page 111, I might ask you, okay, is the function continuous? Or where is the function not continuous? Well, everywhere there's a break, or a hole, or a jump, anywhere there's one of those things, it's not continuous. Anytime you got to lift your pencil, it's not continuous. But if I ask you, why is it not continuous, you can't say a break, or a hole, or a jump. You got to give one of these three reasons here. Okay, so this would be worth looking over again. Okay, so the first thing that has to happen to be continuous, the function must be defined. Okay, the function must be defined. Okay, there's got to be an output. Well, at a hole, there's no output. At a vertical asymptote, there's no output. You have to lift your pencil when you're drawing those kind of thing. Okay, so that's a problem if there's no output. Function must be defined. The limit must exist. So you can't have a break. So again, an asymptote would be a problem. A break, like a piecewise, would be a problem. Okay, the limit doesn't exist. Because at break, there is an output, but you still have to lift your pencil. So, so the limit has to exist. And then those two have to be the same. The limit has to equal the output. So a jump has an output. The limit exists. They're just not the same thing. Right? The cars meet, but the diner's not there. It's in a new spot. So there is a diner, and the cars meet, but they don't meet at the diner. Or it used to be, I guess, to be the analogy. All right, so you need those, all three of those to happen. So like in a polynomial function, all three of those happen. On a cubic, right? Cubic's nice and smooth, nothing weird going on. The limit exists everywhere. It's just whatever the output is the limit, right? So we would rarely even ask you a question about a polynomial function with a limit because it's just boring. Or the sine function, right? It's just boring. It's the limit exists everywhere. So those are continuous functions. All right. So that's pretty much that as far as those things. So let's practice a few things. So let's say I said to you, a lot of times in the directions I just say this. Justify this limit. Like, for example, I've already given you the answer, right? Sometimes I don't do that on these problems. I give you the answer, but I want to see your work of why it is. I just say table, graph, or algebra. Well, it depends. If this is a no calculator one, you're going to use algebra. Well, it turns out there's no algebra we can do on this. There's nothing that'll factor, cancel. Of course, we should start by putting in pi. Sine of pi is 0. Pi minus pi is 0. 0 divided by 0. Okay, that means keep going. Well, we can't do any algebra, right? I have no idea. Graph. Typically, if I'm given a graph, I'll do it, but otherwise I'm going to go to the table. So let's get your calculators out, and let's assume this is on the calculator portion of the quiz, because I wouldn't give this to you on the algebra portion, okay? And let's, Maya, be the presenter.
Okay.
Thank you. All right, so where are we going to go here, everybody? We're going to go to our graph screen, right? Take out any old graphs if you want, and we're going to take this part right here, and we're going to graph that, right? Now, this limit might have had W's in it, or H's, or this might have said as Z approaches pi. W approaches pi. But when we put it into our calculator, we use X, right? So we're going to put that part into our calculator. Okay, just like that. And the window doesn't really matter, does it? Because we're going to go to where now? We're going to go to our table, right? Like if she tried to trace at pi right now, if she tried to trace at pi, we would get undefined, right? Because it's 0 divided by 0. Okay, so we're going to go to our table, and then where are we going? To our settings, right? So we're going to go to menu and table settings, and we're going to start this out where? Where's our table start going to be? It will not be 0. It's x approaches pi. Now, many times when you've done these, that worksheet you did, almost every one on that page you started your table at 0, because every one of those was the limit as h approaches 0, or the limit as x approaches 0. right? But not all limits approach 0. This one is x approaches pi. So we want to do our table start at pi. Now you can do 3.14, I suppose. But the problem with that is the rounding. It's probably not going to give you the undefined that you're looking for in pi. So I would rather you put in pi. So very important that you do that, right? I understand most of the time you've done these, you put a 0 as your table start. That's only because the limit was as x approaches 0. Okay, very important to understand it. All right, so go ahead and hit OK. And then we arrow up a little bit and move our mouse out of the way. There you go. All right, and what do we got? We got undefined at pi, which we expected, but pretty convincing evidence. However, now this isn't scientific because it wouldn't have a 0 here, but go ahead and click on or arrow over to one of those. And we talked about, I think we talked about this, I know I talked about it in the other class. You should, to be certain, you should look at this because you can't see all the digits. So if it said 3.4 something something, you might think, hey, it's going to 3.4. But if you put it up, if you put your cursor actually on there to that cell, it says 3.4 times 10 to the 10th. Well, what does that mean? It's going to infinity, right? That means you must have like vertical asymptotes, and that's where I would say does not exist. If they're going to infinity, so even if both sides are going to infinity, if you said infinity, fine, but for us right now, if we got infinity, we're going to put does not exist. What if this would have said like 3.4 times 10 to the negative 10? What's that? No, not 10 to the negative 10. What's that? That's 0.00000034. Well, what's that heading towards? 0. See, so you do have to be a little careful. So if you get a number here that's like 3.4 and you think, oh, that 3.4, that's my answer. No, you better arrow onto that and see, because it might be 3.4 and then 10 to the negative 10th or negative 6th or whatever. Well, that's 0.0000. That's heading towards 0. Okay, so you got to make sure you understand that part of it. But this one isn't. Pretty clear that the answer is what? It's heading towards -1. Now, I already told you that answer. So what I want you to write down is this table. I want you to copy this table onto your paper, right? If this was the quiz, that would be your justification, okay? So the question was, use a table or algebra or something to justify this limit is -1, and so you would put your table down on your paper with your X column, your Y column, like that, and that would be your answer to that problem.
How many digits would you want us to go to? Because it's the same.
Yeah. Yeah, if you go 999 out to 3. I mean, on these tables, 4 or 5 wouldn't be bad. A few more would be bad, but for sure out to 3. Okay? So there you go. That's all you got to do. That's all you got to put on your paper on one of those calculator limit problems, is just the table, right? And like I said, I'm probably already going to tell you what the limit is because I know you got your calculator. You can just type into your calculator the limit. I don't care about that. What I care about is showing why the limit is -1, and the table does. Yeah.
Can we actually limit full definition for justifications? How it was the
No, that's different. That's different. This doesn't have anything to do with derivatives. It's just a limit problem. Okay? This one doesn't have anything. This does not even look like that f of a plus h minus f of a, right? That's totally different. Like the worksheet where they looked like the derivative, right? You get some of those, but that's not what we're doing here. Okay, now we are going to right here. Okay, so let's say we have this problem. So here's another review problem. This is another thing you're going to have to be able to do. Okay, so f of x is equal to sine x. I want to know what f prime at pi 6 is. Okay? However, I want you to do it by using the definition. So use the definition to set up your limit, then use your calculator using the table. Now when I say use the definition, right, we all understand what we're talking about. We're talking about this guy right here. Well, this guy actually, it doesn't matter. What are we going to put in place of the x or the a here? Pi 6. Right? We're going to put pi 6. So you need to set up this guy right here, okay, except put pi 6 in place of the a. Okay, go ahead and try it. The definition of the limit, or the definition of the derivative. Okay, so when you hear definition of derivative, you all got to know that's that f of a plus h, that whole thing. Okay, so here's what mine looked like. So f of a plus h, f of pi 6 plus h, it means take pi 6 plus h and plug it into the function for x. So you'd have sine of pi 6 plus h minus sine of pi 6 all over h, right? Limit as h approaches 0. Now we take that black thing and we do what? Plug it into our calculator. Use your calculator to evaluate. So the direction said, use the definition of the derivative to set up your limit. So that's what I just did there in the blue. But there's no algebra we can do to this. There's no distributing we can do. This isn't multiplication. You can't distribute sign. That doesn't work. There's no algebra, no factoring, none of that we can do on that problem. So we now can go to our calculator and plug that in, but we can't use h's. We got to do what? We got to use x's. Okay? No, except, no. In the graph screen. So we're doing the same thing we just did. Right? So we're doing the same thing we just did. We're going to take that thing I've circled in black, and we're going to put that into our graph screen, and we're going to do a table. Right? So we take this part, we put that into our graph screen, and just like the back side of the worksheet that you worked on, well, should have been working on for today, right? that I had given you yesterday. Actually, but I had given you the limits. The difference on that worksheet is I gave you the limits, and you were supposed to do it backwards. Which function was it that created it? What was your a value? Here, I gave you the function and the a value, right? I gave you sine x, gave you the a value pi 6, and told you to set, but because quite honestly, that's more likely what I'm going to ask you on the quiz, because that's what I care about that you can do, that you can use the definition of the derivative to set up a limit, okay, and then go. All right? So now we go in here and look, okay, she's got it typed in. She's going here. Now, where's our table start on this one? 0. Limit as h approaches 0, right? Not pi 6, that's different. That's the a value. That's not what we care about. We care about where the limit as h is approaching 0. So we put a 0 in, and what do we get? 0.866? Oh, yeah, 0.866. I wrote that, 0.877. It's 866. Okay, now arrow over to there, though, Maya. Arrow onto that. Let's make sure we don't have a scientific notation. Of course, we're not going to if it's 0 point something. So it wouldn't be, but 0.866 seems to be solid evidence that this is 0.866. Now, and then that's what you would put. Now there you'd want to have, to give your answer, you'd want 3 decimal places, right? So we go back over to here, and so what is this? Well, it's 0.866 to 3 decimal places. Pretty solid evidence on both sides that the cars are meeting at 0.866. Now, look what I did in red over here. We all know the derivative of sine is what? Cosine. So if we wanted to find f prime of pi 6 by the shortcuts, the derivative of sine is cosine, and what is cosine of pi 6? Root 3 over 2, which, I was wrong here, it's not 0.877, it's 0.866, right? So, not surprising that that's the answer that we got. But this would be the shortcut. 90% of the time in this class, that's what we will do. If we want to find out prime of pi 6, we'll do the derivative rule, and then we'll plug in a pi 6, right? But by the definition, we're doing it this way, okay? So, got to be able to set those up using the limit definition of the derivative, okay? All right, let's do this one real quick. Go ahead and, again, use the definition of the derivative. So let's set this one up.
We can't use a shortcut on that, because that's his definition.
Right, can't use a shortcut on that. Now, if off to the side you want to, use a shortcut, and it's going to be 6x squared, the 3 will disappear, plug a 2 in there, 2 squared is 4, 6x. Okay, we better get 24 as an answer, right? The shortcut would be 24, right? I did the derivative, plugged in a 2. That's not what we're doing. We're using the definition of derivative, and that's what the directions will say. Now, at any point, I'll do bits and pieces. If you want to look up here, if you just make sure you're on the right track, you can do that. Or if you'd rather not look up here and get it done yourself, that's fine. Got another step up there if you want to double check. Again, you can make these up. You want to practice these, you can make these up all day long, right? Now, I wouldn't go higher than cube. I would keep it with squares and cubes at the highest. You can make up a polynomial, a quadratic, or a cube function. Make up an a value. You can just practice these all day long. If you need practice foiling out a cubic, or or squaring, or whatever, you can just make up your own. And of course, the shortcut. So you know what answer you should get, right? So you can just spend 2-3 hours at home tonight just making it up, practice all night long, right? Now, I just did the 2 plus h cubed in my head with Pascal's triangle, but you might have a little more work to show there. 2 plus h times 2 plus h times 2 plus h. Don't forget, f of 2 plus h, you put a 2 plus h in for the x. Don't forget the 2 on the outside. Don't forget the plus 3, right? And then here I just did that part in my head. 2 cubed is 8 times 2 is 16 plus 3 is 19. So The 19 was just f of 2. And then I had to cube out that 2 plus h. Then I had to distribute the 2. And so that's all that work over there. Then the 19s cancel. So then you get this, that last thing I have at the bottom, and then I didn't show it, but I took out an h, canceled the h's, and then that just left me with this 24. And then of course those parts, don't forget, h is approaching 0, so we get to the end, you let h go ahead and equal 0, and then boom, you're left with 24, which we knew should be the answer on that. Okay, so definition of the derivative, be able to set up a derivative using the definition, and then you might get to use your calculator to do a table like we did in the last problem, or you might have to do some algebra, in this case the factor and cancel method, right, to find it as well. Okay? All right, so I'll move on from that and you can finish it. But any questions on my algebra there? Yes?
You go over Pascal's, right?
Yeah, again, if you don't like it, just go 2 plus h, 2 plus h, and then get that, and then take that times 2 plus h. You know what I mean? But Pascal's triangle, the row for cubed is 1, 3, 3, 1. So it would be a 1, and then the first thing cubed. So it's 1 times 2 cubed, and then it would be a 3 times the first thing squared, and then the h to the first, and then it would be a 3 from Pascal's triangle, and then be the first thing to the first, and then the h to the second, and then it would be a 1, and then the last thing cubed. And so that's where Pascal's, that's the 1, 3, 3, 1 is where Pascal's triangle comes in. And then it's 2 cubed, 2 squared, 2 to the first, and then no 2's, then no h's, h to the first, h to the second, h. That's Pascal's triangle. Okay, and so that's just a quicker way to cube it out. But if you want to do it that way, do it that way. But again, for time, maybe I'll put a cube on there. But you're gonna have maybe some problem there. It'll take you a little longer to have to think about. So maybe it's that one, but I can't do it with everything, right? Or the quiz will just take too long. So chances are good it would be more like a square or something where you wouldn't have quite that much stuff to do. Okay, but cube would be as high as I would go. Okay, all right. So shortcut. Let's do a couple with shortcuts real quick here. Okay, so let's do a couple with shortcuts. So here's f of x. You guys find f prime. Okay, here's f of x. You guys do f prime. And again, you can make these up all day long too. And you can use your calculator to check them, because I showed you how to do derivatives on your calculator. So just, I put some with x's with negative powers, because that's what you'd have there, or x to the bottom, whatever. So here's f. You find f prime. I'm not going to do any antiderivatives on the quiz. We talked about it a little bit. That'll be the next quiz, so don't worry about antiderivatives. That if it does not say use the definition of derivative, then you are using the shortcut. I think it's important when you do these that you label. So first thing I got to do is rearrange. I got to rewrite that first thing. I can't leave it x to the fourth on the bottom, right? You're not going to take that x to the fourth and just go, oh, that's 4x cubed, and throw that on the bottom. Doesn't work that way. Doesn't work that way. Okay? You've got to rewrite it so that it looks like x raised to a power. So you got to bring that x up like that. Now that is still f. All I've done there is rewrite it. I haven't done any derivative yet. So the derivative is going to be 6x plus what? 20 to the negative fifth, because you're going to drop that by 1, so you're going to decrease from negative 4, you're going to subtract 1, that's negative 5, then leave it. Don't start rearranging, moving the x down to the bottom, because then who knows what you might do. You might put that x, you might do something like I've seen people do this. They go like this, and then they put that x on the bottom like that. That would be awful, because now that's wrong, right? That doesn't go under everything. It only goes under this part of it, right? So don't even mess with that. Just stop right there. Just stop right there. Okay, good enough. All right, try it out. Okay, get it written down, and don't look up here. I'm going to work it. Don't look up here until you absolutely need to. How many people forgot to kick out that 5? Yeah, you have to raise your hand. Right? Yeah, of course you did. I haven't done very many of those. I haven't talked about that for a while. Right? When you're multiplying on the inside by something, remember the inside always stays the same. The inside always stays the same. So you do your derivative, normal power rule, the inside always stays the same. But when you're multiplying the x by some number on the inside, that compresses that graph, which remember, that makes those slopes steeper. It changes those slopes by whatever factor that number is. You've got to kick that out and multiply by it so it makes those slopes change their value. So, 5x inside the square root, first got to write it as a power. And the x minus 5 squared is already how we want it. Bring the 1/2 down in front, drop that by 1, which makes a 1/2. We always leave the inside alone, but when you're multiplying on the inside, when you multiply that x by some number, you have to kick out that number every time. Now, over here, we bring the 2 down in front, drop that to a 1. The shift to the right of 5, that doesn't change the slopes, it just moves them. So that's why we leave the minus 5 in there. We leave the inside alone. We always leave the inside alone. But we don't kick anything out because it didn't compress anything. Okay, only when you're multiplying on the inside by some number. Now you might say, what if you're dividing? Well, don't look at it that way. If you've got x over 2 on the inside, how should you write that? If you have x over 2 on the inside, don't write it x over 2. You should write what? 1/2 x. See, if this problem would have said, if this would have been x over 4 to the 1/2, I would not have done it like that. I would have done it like this. Right? So I never think of you're dividing the x by some number. Don't think of it that way. If you're dividing by 4, what you're really doing is times it by 1/4. So what are you going to kick out? A 1/4. You'll kick out a 1/4. Okay. So if you ever see that, we always want to write it like that because of that rule right there. It just makes it a lot easier to understand. Okay. So we never think about dividing on the inside by something, by a number. It's always multiplying. Okay. And then yes, you should simplify this. If you have a 1/2 here times a 5 over here, you should take those two times each other and write 5/2. Okay. All right, so those are a couple problems. Pretty simple one here, a little trickier one here. You'll probably give partial credit, so let's say you screw that one up, but you do this part fine. So, you get a point for getting that part right. Maybe lose a point for the other one. All right, one more. Yeah, one more. Then let's work on some of these algebra limits here. So anything to kick out? There is on the second one, right? A lot of times we miss that one. You got to kick out a what? -1, because there is a -1 multiplied by that x on the inside. Anytime you're multiplying on the inside by multiplying the x by some number, you have to kick that out. Now, I guess you could argue we're always multiplying by something. Like here, you're multiplying by a 1. That's true. Kick out a 1. Big deal. Doesn't do anything, right? Multiply by a 1. Doesn't change anything, so we don't worry about it. But in this case, the negative does change things. Now, I think you should then take that -1, swing it around and put it on that 1/4 and not leave it over there. So for a final answer, I think it ought to look like that. Okay? Now, on this quiz, make a big deal about that, probably not. We get to chapter 3, where we're actually going to do a quiz. That's all it is, or the shortcuts, the derivative. That's the whole thing. Then, yes, you're going to have to write. You're going to have to make sure to do that. Okay? Not as big a deal. Okay, first crack. All right. Let's talk about some limit problems here. So let's go through a couple. We can kind of go through them together here a little bit. I'll give you a little time to get started. This is clearly when you look at this. So this isn't anything to do with derivative. This isn't definition of the derivative, right? This is just a limit problem. This is just a limit. It doesn't look anything like f of a plus h minus f of a. It doesn't look anything like it. Doesn't matter. It's just a limit problem. We're going to do it. Now, the first thing you do is plug in a 3, right? First thing you do is plug in a 3. What do you get? 1/5 minus 1/5 is 0. 3 minus 3 is 0. You get 0, 0, which tells you to keep going. Which the keep going in this one is what? There's a bow tie. Okay, go ahead and get started with it. Then I'll see if you can see how far you can get with it. Okay, just because of time, I want to get through some stuff here. So we're going to. Everybody see where that -1 came from? These cancel right here. You got to take out a -1. 3 minus x, x minus 3. If you take out a -1, that'd make -3 positive x, which is that. That cancels. But remember the invert multiply thing we talked about? Invert multiplies. I got the x minus 3 on the bottom, so we flip that up. And then we can cancel those right there. But we got to take out a negative. So that's where that -1 came from. Then we got this. This is gone, of course, because I flipped it up over there. Right? The bow tie parts start here. 5 times 1 is 5. X plus 2 times 1. But you're minusing, so you got to put parentheses around it. Distribute that negative. 5 minus x minus 2. 5 minus x minus 2. So that becomes 3 minus x. So that's where the 3 minus x came from up here. Okay. Over that. And then the x minus 3. Invert, cancel, but had to take out -1. Now we can plug in our, what I do at the very end then. Plugged in a 3 for x. X approaches 3. So I plug in a 3 right here. 3 plus 2 is 5. 5 times 5 is 25. -120. Okay? That's the bow tie. Okay? Here's your conjugate. Try that one. Again, plug in a 1 first. You get 0 divided by 0. So that tells you to keep going. Sometimes in the bow tie, people think you got that square root of x plus 3, and they want to change that to an x minus 3. That's not what we're doing, right? It's radical minus something. Sometimes it's radical minus a radical. Sometimes just radical minus some number. Okay, so that's why I always just say radical, because that never changes. Whatever that radical is never changes. So it's radical minus 2. We want to multiply it by radical plus 2. Right? Radical minus 2. We want to do radical plus 2. Top and bottom. Right? Because when we FOIL that top, remember what happens when we FOIL this. This times this just gives us x plus 3. The outers and inners drop out. -2 times 2 is -4. Okay, the bottom we just leave in its factored form. Why? Because something's going to cancel. So we leave the bottom as x minus 1 times that quantity there. And sure enough, look what happens on top. We get x minus 1. That doesn't happen every time you do a conjugate, but these problems are set up nicely so that this happens, okay? So you get x minus 1 on top, x minus 1 on the bottom. Those cancel. Now you can plug in your 1 for x. So when the x minus 1s go away right here, 1 plus 3 is 4, square root of 4 is 2, 2 plus 2 is 4. You still have a 1 on top after these things cancel. So after you cancel those things, you still have 1 up here. Put in your 1 right there. 2 plus 2 is 4. Okay, questions about that? Okay, so you got bow tie, you got conjugate, then of course there's the factor and cancel thing, which is what we saw when we did this one back here with the h's. This is what happens here where you get some stuff you can factor out. So that's always the easy one. So bow tie and a conjugate. Okay, last thing. So that's taken us through the calculator tables. I mean, if you go back to what we put up here at the beginning, we've pretty much done all this. We talked about setting up the definition of derivative. We did it with a calculator table. We did it with algebra. We talked about the graphs or the cars meaning. That's pretty easy. We talked about whether a function's continuous or not, the things it has to have here, what violates those. We've talked about our shortcuts, how we do those. Okay, now again, any limit we can do with a calculator table or algebra could be one of those special limits that are like this, that we set up with the derivative, or it could be just a plain old limit problem that we can do with algebra or we can do with the table. Okay, so, and then the last thing was this idea of max and min. So let's throw this problem up here. So section 4, 2.4, is where we brought in the big F notation. So don't forget about 3 through 12, problem 3 through 12 and 2.4 that we did on homework the other day. Be able to do some chart kind of questions with big F notation. We should talk about that earlier. So understand that notation and so forth, okay, and be able to answer a question about that. But then what if I gave you this function here and said find any local max or min, right? Find local max, local min. Where's this increasing? Where's this decreasing? That's just our sign analysis, right? That's our F prime number, okay? So, and this could be on the calculator part or the no calculator part. Depends on how easy the function is, or maybe I just want to balance out the problems, whatever. Your work should look the same no matter what. Remember, even if it's a calculator problem, that is not permission to just graph this and see where the local max and mins are. That's not what this is. You've got to do your sign analysis, your number line, and show all that work, okay? The only thing you can use your calculator for is to maybe solve the equation. Well, that's actually what's going to happen here, because watch what happens when we do the derivative. We're going to get 3x squared minus 2x minus 6 equals 0. Now, I picked this one on purpose. If we tried to factor this, 3x and x, let's say we went 2 and 3, that'd be 3x, 6x. That won't give us 2x. Let's switch them. 2 and 3, that'd be 9 and 2. That won't give us 2. Let's go 6 and 1. That'd be 6x, 3x. That won't give us 2. If we switch it 1 and 6, 18. There's no way. That doesn't factor, okay? So if it's a no calculator one, if I put it on the no calculator, then for sure it's going to factor, okay? And it's just going to be a nice one. It'll factor. You'll go from there. Okay, if I put it on the calculator part, maybe it'll still factor, so you can try it if you want. But just grab your calculator and do a solve right now. Everybody, let's do that. Grab your calculator and let's just do a solve. So you don't have to show any work for this part. One of the things you're allowed to use your calculator for is to solve an equation. You have to have the equation on your paper, so you got to make sure you do your derivative, set it equal to 0. That's got to be on your paper because you get points for that. You're going to get a point for doing this derivative and putting it on your paper. Let's get decimals here. Now remember, your final answer just has to have 3. You can round it when you write it down. I don't care when you're in the middle of the problem. But your final answer has to have 3. So hit Control Enter if you're probably getting some square root ones in, right? Because isn't that kind of a weird one? So give me the two numbers. Who's got it? Haley, you got them? What do you got?
Negative 1.119. And then 1.786.
You guys agree? Okay. And again, rounded is fine or truncated is fine too. Okay, on that third decimal place. All right. So those are our two stationary points. This is where the derivative is 0. So we either have a flat spot, a local max, or a local min. Right? We're now going to test to see which one of those we have by doing an F prime number line. We're going to put negative 1.1 on there and 1.7. See right here, I don't care if you put 3 decimal places here. This is just your number. Okay? So what numbers do you want to pick? Well, how about negative 2 over here? How about 0 over here? How about 2 right here? Right? Now, there are some shortcuts on your calculator I could show you, but you got enough to work on for the quiz tomorrow. I'm not going to mess you up with that right now. So you just need to put a negative 2 into this, and then a 0 into this, and then a 2 into this. Well, you could do that even without your calculator, right? Negative 2, that'd be 4, that'd be 12. Plus 4 is 16. 16 minus 6 is positive. 0 is going to be negative 6. Put a 2 in there, you're going to get 12. Minus 4 is 8. 8 take away 6 is 2. So you're going to get a positive. So you can type those into your calculator if you don't want to do it in your head. Afraid you might make a mistake, whatever. Okay, now, again, yes, don't we know this is a cubic? We know it's going to go up, then down, then up. Okay, so, but maybe there's a flat spot in there, right? Maybe it's one of those that comes up and has a flat spot, or maybe this is plus, plus, plus. Maybe it's just increasing the whole time, right? I mean, well, we know you have 2 flat spots because the derivative's here. But it turns out those are local max min. And don't forget how I said you have to write this. If it wants to know where is it increasing, then you would say negative infinity to negative 1.119 right? If we want to know where is F increasing, if that's what they wanted to know, where is F increasing? Well, negative infinity to negative 1.19 and from 1.786 to infinity, right? That's where F is increasing, if that's what they wanted to know. If they wanted to know local max, that's when we would say at x equals negative 1.119, F prime changes, they would probably say justify your answer. F prime changes positive to negative, so F changes increasing to decreasing, right? That's what we said. If you're giving a reason why something's a local max, you have to write that out. The local max is there because F prime changes positive to negative there, so therefore F is going to change from increasing to decreasing. Okay, there you go. I mean, that's a pretty good review of that stuff. The review problems down at the bottom of your assignment sheet are not that great. It might just cause more confusion than be helpful. However, there are a couple. If you turn to page 150 and 151, 23 through 26. 23 through 26 are just doing kind of some shortcuts. But to be honest, 25, we haven't even talked about those derivative rules. Well, cosine we have, but not natural log. So 25 you couldn't really do. But like 23, 24, 26, those would be like practice doing the shortcut. But like I told you, you can make those up on your own, right? You can make those up all day long. And then
Kearney High School. Wanted to announce our Outstanding Student of the Week this week. It is Tracy Tran. Tracy Tran is our Outstanding Student
41,
of the Week. If you
41,
see Tracy in the hallways or if she's in your class right now, give her a high five, congratulate her on this awesome accomplishment. Thanks, everybody. Have a great day.
There aren't really very many in there that are that good for what we're specifically doing, okay? So some good practice on the algebra stuff, that worksheet that I gave you. I'll try to get an answer key, a worked out answer key up online at some point. But like I said, my plan period's used up with meetings today, so I'm not sure how that's going to go. And Bearcat time, so that's when I would usually get that done. So I'll try to get that put up there. But remember, on that algebra, on that worksheet I gave you today, the backside especially is where you're using that algebra. The bow tie, the conjugate, that kind of stuff. You can type those into your calculator just the way they're written there with the limit notation and everything. I'm not talking about doing the table. Well, you can do that too. But I'm just saying, just to get the answer, you could literally type in on your calculator screen, not on the graph screen, but on the calculator screen, you could literally type in that limit and just see what the answer is, right? You could do the function part of your graph screen if you want to practice that and use the table to see when it's supposed to be 2. You could do that, okay? So if you're working it out and you think you did it right, that'd be a way you can check, okay? And then I'll be here early in the morning if you want to come in and check things over and ask me any questions on those. Okay, so that would be good practice for that. You had number 20 in your homework was a local max min kind of sign graph. You could do 21. I think we did 19 the other day. So you could do, or did we do 21? We did 21. You could do 19. Number 20 I assigned you do 19. That's a good one. So you can do that. For the local max min, there's the bow tie stuff, the shortcuts. I showed you some of those in the review problems. Again, you can make up ones like this all day long too, right? Just a squared or cubed at the most with your definition of the derivative. Here's one with the calculator table. Even this one we did with algebra, you can do with the calculator table, right? Once you got this set up, the part in black right here, we can type that into our calculator. Right? You can type that part into the graph screen. Type that part into the graph screen, except don't use H's, use X's. and then see where that, see if that's approaching 24. So you can practice both your algebra and your calculator part with that. There we did the table again. So, okay, that's pretty good review of everything right there. Okay. Just in time.
So Jeff, we'll just take scheduling notes.
Yeah, just get ready for the quiz tomorrow. I'm sure we'll do. We do have, I probably have about 2 minutes. There's an extra credit. If you've had a brother or sister in calculus or a friend, you may have heard the day, our last day before Christmas break, you have an extra credit opportunity if you want to write and perform a calculus carol. Or you don't have to sing, it could be a poem, 'twas the night. But you have to make it calculate, it has to be original lyrics, not something you stole off the internet. You can get ideas there. I'll probably show you some from previous years because I have to videotape you too. You get videotaped. You might get shown to next year's class.
But you have to
So like, say, for example, a poem, like you could do, 'twas the night before the calc test. That's a popular one. Or, the song from The Grinch. Trust me, I've been called The Grinch many times, for extra credit. Or whatever, okay? So you have to write your own lyrics that have something to do with calculus, and then, so bonus points, bonus opportunity. So you got 4 weeks to think about that.
How much extra credit?
Oh, yeah.
Well, my